Hey everyone, today we're going to go through accumulation functions, and the problems we're going to go through in the video are very similar to what we did in class today, but I think because this is a fairly complex topic, it's kind of good to see it again. So just as a reminder, when we talk about an accumulation function, we're really just talking about any function that is defined as the integral of a different function. So as we go through this topic, you're going to see functions that look like this. So it's defined as g of x, but g of x is going to be the integral of another function, and I'm going to say f of t dt. And typically we'll have a lower bound that's some number and an upper bound that's x. So you can see that g is defined as the integral of f, and then g of x is what we call our accumulation function. So as we go through the notes here, we're going to kind of go through all the different types of questions that you could be asked about these accumulation functions. So let's dive in here. So my first problem says f is a function defined on the closed interval from 0 to 7, and I'm given the graph of f here, which consists of 4 line segments. Now they're giving us g as the function given by the integral from 2 to x of f of t dt. So you can see g is my accumulation function, and I have the graph of f. So the first question they asked me is to find g of 3. Well, I know that g of 3, if I go to my function definition here, is going to be the integral from 2. Now my input is 3, so it's from 2 to 3 of f of t dt. Right? Now we have to think back and remember, I know this integral is really just the area between my function f and the x-axis between the interval from 2 to 3. So if I look on my graph here from 2 to 3, to me it looks like I have a kind of sideways trapezoid here. So the height of that trapezoid is just going to be 1. So I have 1/2. Base 1 of that trapezoid is going to be 4. My base 2 is 2. So I have 1/2 times 6, which is just 3. So g of 3 I know is 3. Now the next question is asking me about g prime of 3. So before I worry about 3, I'm just going to deal with, well, what's g prime of x? So g prime of x I know is going to be the derivative, so the derivative with respect to x, of my integral. And hopefully pretty quickly we should be realizing that this is just the fundamental theorem. Right? Fundamental theorem of calculus says, well, what I do to find that out is I plug in the upper limit. So I have f of x times the derivative of x, the derivative of x, which is just 1. And then I subtract f of 2, but the derivative of 2 is just 0. So what I know is that g prime of x is just equal to f of x, which actually simplifies things a lot for me, because now I know that g prime of 3 is just equal to f of 3. So if I look here, f of 3 is equal to 2. Now, while I'm here, I'm going to make a note. We just found out that f is really the same as g prime. And so that might help me later, because when we start analyzing this graph, we're just going to treat it like when we're analyzing the graph of the derivative. All right, so last but not least, now I have to find g double prime of x. Well, if g prime of x equals f of x, then I know g double prime of x is just f prime of x. So now g double prime of 3 is equal to f prime of 3. What this is saying is if this is my graph of f, f prime of 3 is the slope of f at x equals 3. So we're just going to be really using rise over run here. So f prime of 3 If I look here, it's linear, so I can just find rise over 1. I go down 2 over 1, so that slope is a negative 2. So my biggest, I guess, piece of advice would be here, especially when you're finding g prime and g double prime, is to just first find that in terms of x before you go plugging in the values, because that generally will simplify the problem quite a bit. All right, so now we're going to get into some meatier stuff here. So in part D, it's asking us to find the critical points of g. Now that's important, right? They're going back to this function g, not f. So I have to be careful how I approach this. So find the critical points of g. Well, I know that's going to be where g prime of x is 0 or undefined. And then it wants to know where g of x is increasing. I know that's going to happen where g prime of x is greater than 0, and where it's decreasing is where g prime of x is less than 0. So let's look at these separately. So my critical points, I said, is where g prime of x is equal to 0. But now here I want to stop and think. We found up here in part B that g prime of x is really just equal to f of x. So what I'm really looking for is where f of x is equal to 0 or where it's undefined. So if I look at my graph of f here, I can see I'm equal to 0 at 0, at 4, and I'm equal again at 6. So those would be my critical points, and you can't see that. Sorry about that. So at 0, 4, or 6 are our critical points. Now, where g of x is increasing, we said that was where g prime of x, which I actually know is f of x, is greater than 0. So I'm looking for where is my graph above the x-axis. So now that I know that, I can pretty quickly tell that those intervals are from 0 to 4, and then again from 6 to 7. Okay, then the last piece is where g of x is decreasing. Now in this case, we know that's where g prime of x, which is equal to f of x, is where that's less than 0. And again, looking at the graph, we can tell pretty quickly that's going to be on the interval from 4 to 6. All right, so those are basic questions we can be asked. We're going to go on the next page. We're still working with the same graph, and we're going to get in a little bit deeper here. Okay, so again, I have my same function here, defined by it's the same accumulation function here. And now in part E, we're looking for the x-coordinates of the points of inflection of g of x. Now, here's where we have to remember about points of inflection. If I'm looking for the points of inflection of g of x, I know that's where g double prime of x is equal to 0, or where it's undefined. That's my first criteria, but I also have to look and see that g double prime of x changes signs at that point. So it's not enough that I'm just 0 or undefined. I have to make sure I'm changing signs. So let's go ahead first and let's look at our possible points of inflection. So when we were talking about this, we said g double prime of x is equal to g prime of x. Sorry, I wrote that wrong. G double prime of x is equal to f prime of x. So what I'm looking for is where f prime of x, the slope of f, is either 0 or undefined. So I'm going to make here g double prime of x equals f prime of x equals 0 or undefined. Now remember, undefined is going to happen where I have a corner, cusp, or a vertical tangent. So first thing I'm going to do is look and see f prime of x. See if that, see if the slope of f is either ever equal to 0. And so I don't see any horizontal tangents, so I don't have that, but I do see some places where it's undefined. So that slope of f is going to be undefined at 2, at 4, because I have another corner point there, and then again down here at 5 with corner. So that's where my f prime of x is undefined. However, we said in order to call it a point of inflection, I have to know that that slope changes signs as well. So let's look at x equals 2. My slope, so f prime was positive, and it changed to negative. So that's going to be a point of inflection. Now, down at 4, my slope was negative, and it stayed negative. So 4 will not be a point of inflection. So we're going to cross that out. So when we talk about points of inflection, we're going to keep 2. 4 we said was not. Now if I look at 5, the slope changes from negative to positive. So that is going to be a point of inflection. So now the next part of this talks about concavity. So I'm going to be concave up. I know that's where g double prime of x, which we know is f prime of x, is greater than 0. So where f has a positive slope. So I'm going to be concave up from 0 to 2. And then again here from 5 to 7. I know I've got a lot going on here, so I'll box this up. So now, on the other hand, when I'm looking at concave down, that's going to be where g double prime of x, which is f prime of x, is less than 0. So here I'm looking where f has a negative slope. And so that's going to happen from 2 to 4, and then from 4 to 5. Okay, next part. Now we want to know the x-coordinates of the absolute maximum and absolute minimum values of g. So at this point, we're kind of beyond looking for critical points, and we want to know about those absolute extreme values. So again, if I'm looking for the extreme values of g, I'm looking for where g prime of x equals f of x is equal to 0. And so my critical points, and we found this earlier, found that our critical points were at x equals 0, at 4, and at 6. Now, because I'm on a closed interval, I need to consider not only these interior points, but I need to consider what's happening at my endpoints. So I'm going to make a table here. I'm going to find x and g of x. Again, I'm going to include my endpoints, 0, my critical points, and I'm going to include 7. And now we're going to calculate those values of g to find out where our absolute extreme values are. And to do this, we're going to have to use the definition of our accumulation function. So for g of 0, what I'm calculating is the integral from 2 to 0 of f of t dt, which I know is going to be the opposite of the integral from 0 to 2. So now again, we're just with this integral looking for an area. So from 0 to 2, luckily that's a nice easy triangle. I'm going to keep my negative. I have 1/2 times my base of 2, and then my height is 4. So I have a value of -4 at x equals 0. Okay, now we're going to calculate g of 4. So I have the integral from 2 to 4. And I'm sorry, this is pretty tight here. F of t dt. So from 2 to 4, again, I have a nice triangle here. This one, I don't have to worry about the negative. My bounds are in the correct order. So 2 to 4 is 1/2. My base is 2 again. And my height is 4. So I have a positive 4. Next up is the integral from 2 to 6 of f of t dt. So if I look from 2 to 6, I'm actually going to split this up as the integral from 2 to 4 of f of t dt, because I have that already, plus the integral from 4 to 6 of f of t dt. So 2 to 4 we found out was 4. Now I'm adding this, but because this area from 4 to 6 is below, we're going to end up subtracting the area of that triangle. So I have 1/2, a base of 2, and then a height of 1. So I have 4 minus 1, which gives me a value of 3. And then last but not least, I'm going to calculate the integral from 2 to 7 of f of t dt. And again, I'm going to break this up. I'm going to take this whole chunk, the integral from 2 to 6 of f of t dt, and I'm going to add the integral from 6 to 7. So from 2 to 6, I had 3. From 6 to 7, I'm adding this triangle. 1/2, base is 1, and height is 1. So I get 3.5. So now I can use my table to fill out, or to find, the absolute max and absolute minimum values. So I'm going to write this down here because I'm running out of room. So I'm going to say G has an absolute maximum value, and let's see, that's going to occur here, of 4 at x equals 4. And then I know G has an absolute minimum value. My absolute minimum is -4 at x equals 0. There we go. So again, what we did was we first found our critical points. Then I knew because I was on a closed interval, I had to include the endpoints. And then I created this table so that I could compare those values, those function values. All right, I know this is a lot. We have 2 more parts to go through, and then we'll be done for today. So let's go ahead and take a look at part G. So average rate of change of G, right? When I see average rate of change, I'm just thinking slope, my regular old slope formula. So if I want on the interval from 0 to 3, this is going to be G of 3 minus G of 0 all over 3 minus 0. So let's see what we have to help us out here. G of 3 we actually found, if I flip back here, on the prior page. So G of 3 I know is 3. I'm not going to recreate that math. G of 0 we actually did in this problem. So G of 0 we found was -4 over 3. So our average rate of change is 7/3. So now it says for our last part, for how many values of C, where 0 is less than C is less than 3, is G prime of C equal to the average rate found in part G? So really I want to know G prime, where does G prime take on the value of 7/3? And so here's what we're going to use. We're going to use what we know. We found out before that G prime of x, Right, again, using the definition of this accumulation function, I know g prime of x is just the derivative of this function, which is just f of x. So what I really want to know, sorry I'm crooked here, is where is f of x equal to, or not where, how many times is f of x equal to 7/3? So just keeping in mind, I know that's 2 1/3, so a little more than 2. So I'm going to go back up here. Now I know that's a y value, so 2 1/3 is about here. And if I draw that in, I notice that I intersect that graph 2 times. So down here now, I can say that g prime of c, which is equal to f of c, is equal to the average rate for 2 values of c, because f of x equals 7/3 2 times. Oh my gosh, I'm sorry, I have not been paying good attention to what you can see. Okay, so we know that f takes on that value 2 times. So there we're just using what we know about the derivative and the graph to find that answer. So I know that's been a lot. Tomorrow, actually the next 2 days, you'll have lots of time to practice and answer questions. So as always, thanks for hanging in, and I will see you tomorrow.